Everyone. I realized that I just did an introduction or muted. Good to see some new people in here. We're just gonna wait about 5 minutes to get some more people in here, and then we can get started. Yo guys, all right, I'm gonna get started. We got a pretty good turnout today, so I'm quite happy with that. Okay, I pushed some changes just about like 20 minutes ago to the repo. So if you could all like download the latest version, because there were a couple of changes I made from yesterday. So I'll link that in the chat. And yeah, let's get started. So just gonna.
That'd be another really good feature that we needed in the chat. It's like clickable links. I'm sure there's like some code for doing that. Yeah. Just like check. Yeah.
Okay, so just launch our notebook.
But yeah, so we can like makes sense, you know, like how to get started with that stuff. So there's like I said, I just finished sending out that finished setting up that form component, and what it does now is it sends a message which
Gonna go to the second lecture, sequence to sequence, and the RNNs file.
And so we need to make a message handler, which a student will have which all users will have to respond to form.
Okay, so today we're gonna look at RNNs, RNNs for language modelings, LSTMs, and then something called the sequence-to-sequence model, which is used in translation. And I hope I'm not muted. Cool. Okay, so we're gonna start by doing a brief recap and primer on RNNs, and then looking at RNNs for text classification. We'll then look at something called bi-directional RNNs, before looking at RNNs and how we can use those for language modeling, and what language modeling specifically is, actually. We'll very briefly talk about the evaluations of language models. I don't want to spend too long on this, before looking at the LSTM, the long short-term memory recurrent cell, and its relation to the RNN, and you know what you should be using and when. We'll also look at the GRU, the gated recurrent unit, but we won't look at this in detail. Finally, we'll look at the sequence-to-sequence model and talk about translation problems. Obviously, guys, I'm going to be checking the classroom every now and then, so please feel free to ask questions. Please use the groups during the code break. And guys, if I haven't seen a question, please just you know, feel free to answer it as well and contribute. Okay, so we cover RNNs, vanilla RNNs, pretty extensively in the deep learning course that we're currently running. Definitely worth checking that out, because it goes into a bit more detail about RNNs themselves, and specifically the backward pass and how we update the weights of our recurrent network. We're not really going to be focusing too much on the backward pass in this lecture, so please refer to the fourth lecture of the deep learning workshop series if you want to understand that in a bit more detail. Apart from that, yeah, let's get started. Okay, so RNNs are designed to make use of sequential data, which is basically where a current step has some kind of relation with the previous steps in our sequence. And this makes them ideal for applications with like some kind of time component, such as audio data or time series data, and natural language data as well, because we can consider each word to be a different point in time, a different time step. And RNNs are a network whose output value depends on the output of the previous input. Okay, so we'll look at an image in a second to clarify that in a bit more detail, but actually, no, let's look at that now. Okay, so this is one RNN cell for one input. What we're going to have is multiple inputs. We're going to have xt, xt plus 1, xt plus 2, you know, xt minus 1, and these are all represented in one cell. So this is just one cell, which means it's for one word, but we see that we have these arrows coming in from the left and going out from the right, and this indicates that there's going to be a cell previously and a cell afterwards, after the current input, right? So we take in something called ht minus 1, which is a hidden state, okay? So this is just a vector which the previous RNN cell outputs, okay? So this is fed in as input to this RNN cell alongside the input that we're currently considering. So this in our in the natural language case would be a word, right? So we have a vector, which is the previous hidden state, which is outputted by the RNN cell of which is outputted by the previous RNN cell by some operation, which we'll look at into a second, and the input for the current word that we're looking at in our time series data. So what this means is, if we had a sentence, the cat sat on the mat, and we're at time step 3, so the cat sat, we have ht minus 1, which is some hidden representation of sat, which is based on of cat, sorry, because we have the sentence the cat sat on the mat, and we're looking at the word sat right now. So this xt would be sat. This ht minus 1 would be some hidden representation for the word cat, which depends, and this is the important part, is it depends on information from its previous time step as well. So the hidden state for the word cat will incorporate some information for the word the from the beginning of the sequence. So this hidden state, it comes in, and remember the hidden state is just a vector, so it's a vector which encodes the meaning up to of the sequence up to the current point in time. So the cat sat on the mat. When we're looking at the word sat, this hidden vector is going to incorporate the meaning of the word the and cat. So this hidden vector comes in, and we concatenate it with the current input that we're looking at, right? So the way that this would typically work is this xt gets passed through an embedding layer, and we looked at word representations in the first lecture. So what we do is we have the ground truth word, so not the ground truth word, the actual concrete word, sat. We pass this through our embedding layer, which gives us like a word representation. So we have a vector for the word sat. We have a hidden representation, and we concatenate the two together. We then feed this into a neural network, which outputs the next HT. So this neural network will output this, the hidden state, which is then fed into the next RNN cell, right? So there would be an RNN cell here, which takes in the next word as input and uses this HT as the hidden state, which incorporates all the meaning from the previous words in the sequence. We also have this, this arrow, and what this is just saying, this dashed arrow, is, okay, well, we might want to use this hidden state to make a prediction as well. What if we wanted to have a prediction for every input in our sequence, right? So an example of this could be like video captioning, for example. We want every input that we have to have some kind of output of it. So this will be the that many-to-many problem that we looked at the other day. So I'll just load up that image so you guys can remind yourselves. It takes a bit long to load. Let's see if we got questions. No questions. Cool, guys. Remember, just feel free to ask questions at any point. Anyway, so if we wanted to, let's say, have this predicted y hat t for every time step, we're looking at this many-to-many problem here, right? Because we have an input, and for that input, we want to output some kind of prediction. Okay, so let's look at this a bit more mathematically. So HT, or I'll read through this first, and then I'll describe it a bit more intuitively. So an input vector representing the current input element xt, which is this xt here, is multiplied by a weights matrix and then passed through an activation function to compute an activation value for the hidden layer of units. This hidden layer, in turn, is used to calculate a corresponding output yt. So what this is saying is that we have some function, and we take in the previous hidden state, ht minus 1, and multiply it by u, which is a weights matrix. We then we add it to w, which is another weights matrix, multiplied by xt. So remember, this w here is going to be our word embeddings, which we looked at yesterday. This u is something that we kind of want to learn during training. And this g represents the function that we have, which outputs the hidden ht at the current time step. So essentially, this g function here is this neural network, right? So our g is a neural network, and then our yt is going to be some activation over the hidden state multiplied by another weights matrix. So this is just another neural network, and this is a linear layer, and this a is an activation function, so a nonlinearity, for example, and the activation function that I've just put here as an example is softmax, but it doesn't need to be. It depends on the kind of problem that you're trying to solve. Okay, so for as a computational trick, we can kind of simplify this equation a bit. We can say that we can concatenate ht minus 1 and xt together and just learn one weights matrix over these two variables. So that means that we'll have a weights matrix of size, hidden size dimensions plus input dimensions. And input dimensions is obviously the same as embedding dimension. So this is embedding dimension plus hidden size dimension. And we specify the kind of hidden size that we want our RNN to use. And the hidden size is basically just the dimensionality of each of these hidden state vectors. Okay, so we introduced the problem of text classification last week. So what we looked at last week, or yesterday for those guys who came yesterday, was how we can represent this input as a series of embeddings, or how we can embed our input and represent our input to feed into our model. So this is what we solved in the previous session, getting this data ready to feed into a model. And what we're going to look at today is actually the model component of this, and using RNNs to actually take in this natural language data and output these predictions. So we're instead of doing this 5-star rating, we're just going to look at the positive, negative, and neutral. So 0, 1, 2 instead of 1, 2, 3, 4, 5. And I just want you guys to know that obviously, this is a multi-class problem, and basically the concepts that you learn by doing this multi-class problem over 3 different classes is just exactly the same theory behind it for when you have like hundreds of classes or thousands of classes, for example. Okay. And we use RNNs over feed-forward neural networks, FFNNs, otherwise known as MLPs, multi-layer perceptrons, because the feed-forward networks do not take context into account, right? So if we look at this diagram again, so this would be the feed-forward network, this one-to-one relationship. So we had a for loop saying, okay, for every word, output a prediction and then average that prediction. It's not going to work as well as using an RNN because we don't have any context in that, right? We're just saying here's one word and output a prediction. We're not looking at the whole sequence in its totality, which an RNN allows us to do. So each word is represented by its embedding, which is independent of other words, right? So this word this x0 goes through an embedding layer, which is then fed into this RNN. This x1 is fed through an embedding layer, which then goes into this RNN, and the embedding layer is just the what we learned yesterday. So here this input goes into an embedding layer, and then this embedded input is what we do what we run the RNN against. And context is important because the meaning of the sentence or on the word or about the word itself can change depending on the context. So, for example, the word mean in these 2 sentences, I compute the mean and his behavior was mean, have 2 different meanings, even though the same word is used. And an RNN can kind of encode like the difference in these 2 definitions. I want to avoid using the word mean there because obviously the pun is great and all, but it might just get a bit complicated. So this example that I give here, it starts off with with a movie review. This movie was something, so this ... just indicates carry on the sequence, and finishes with nor witty. Okay, so we kind of see this nor here, and that kind of negates, the positive things that we thought this review might have said, if we didn't have this nor there, because it ends with the word witty. So if we were doing this with like this one-to-one neural network, we kind of wouldn't have like our network wouldn't understand. Okay, when it sees the word nor, it kind of means we're negating the semantic polarity of our sentence. But an RNN, because we're taking in all the previous context, because this word witty is based on all the previous words, we kind of encode the meaning of we kind of know, or the RNN kind of understands during over a bunch of training, that when it sees the word nor or not or like a negator, the polarity of the sentiment is kind of reversed because we have this negative term in there. So these cells are working these, you know, each one of these orange boxes here is this RNN cell that we see, and the weights of this neural network are fixed. So as in they only get updated during training, but for one sequence these weights are the same. So we feed in the initial hidden vector to the RNN, because each of these RNN cells, so an arbitrary RNN cell takes in as input a hidden vector, but the first RNN cell needs to be initialized with a hidden vector, and this hidden vector is usually just a 0 vector. So we then start the process. So this goes in along with the 0 vector. We get some hidden representation, H0, which gets fed into the next RNN cell along with the word movie. So some computation happens in this cell, and we output you know, the next hidden state. And this carries on all the way to the last hidden state. And because we have a sentiment classification problem, we want to use this last hidden state, which is basically the meaning of our whole RNN, to make a prediction. Okay, so we feed in this hidden state to a neural network which will output a prediction. So output y hat, and let's say, you know, y hat is output as 4, but our ground truth is 2, and then we'll obviously just optimize against the prediction in the ground truth. Okay, so we're going to code this up actually. So we'll just have our standard import. So we're going to be working with Torch. We're going to look at Torch text as well, and I'll explain that in the next code cell. And we're just going to, the seed is kind of useless, but we're just going to set a seed and just a helper function to print the time between epochs. Okay, so Torch text allows us to load in like some pre-specified data sets. So I'm just gonna see if we can find what that is. Not gonna spend more than a minute looking for this, to be honest, because it's not too deep. Torch text data sets. Okay, so we have like a bunch of different data sets for different tasks: sentiment analysis, question classification, language modeling, machine translation, question answering as well. There are a ton more data sets out there for each of these topics, but these are just like some very toy data sets that we can easily use Torch text for. And actually, Andrea, next on Monday, the coming Monday, he's going to be running a tutorial on how we can, you know, load in our own custom data sets using Torch text. So guys, if you're interested in using NLP for practical purposes, definitely come through to that tutorial. We'll send out an email tomorrow, you know, outlining a bit more information about that. But we're going to be working with the SST, so the Stanford Sentiment Tree Bank dataset, and where is that going to be defined? Okay, so that's here. So datasets.sst.split. Okay, but we'll get to that in a second, because let's run through this sequentially. So we have this field object within Torch text, right? So we've imported Torch text.data and Torch text.datasets, and within this data we have this object called field. So our field basically defines the it's basically saying, okay, we're going to have the type of data that we want to have, right? So this is just some text data which we're going to pass in as a what we're going to call our text, and we're going to have a label as well, right? So our training data, for one piece of training data, we're going to have a sentence, and we're going to have a label for it, and this label is going to be like obviously a number. In our case, we're going to be using 0, 1, 2. I'm sure that's mentioned somewhere. I'm sure I mentioned that before as well. So that's why we have this special label field there. So what this is saying is we're going to tokenize using Spacey, which is the industrial language modeling tool we looked at yesterday, and we also want to lowercase everything, right? So kind of by defining this field, we've done our pre-processing. We don't need to look at the regex or you know, the complicated steps that we did yesterday. Torch text kind of allows us to do this very rapidly. And we're gonna experiment with the Stanford Sentiment Tree Bank, which will predict a sentiment for a movie review, and the labels are going to be one of these three labels: positive, negative, and neutral. and we load in the Stanford sentiment tree bank, which is this datasets.sst, and we're saying, okay, so we have the text and label, and we want to split it into train data, validation data, and text data. Okay, and we're just going to use like the default splits, which this splits operator provides us. If we want to look at that, then I think which inherits from there's probably something in here. So splits, which defines what the split is. I imagine it to be 70% train data, 15% validation data, and 15% test data. Okay, I don't know what it is, but that's what I imagine it to be. And we can just print the, we're just going to print the examples of the statistics over the training data. So it'll take a second, probably because SST is quite big, and it might need to download it if you guys don't already have it on your local system. So the first thing we're going to see is look at our train data. So each one of these has the same objects or the same attributes attached to the object. So our train data object has this attribute called fields, and fields, as we can see, is text and label. So text and that just comes from text and label. Actually, I think it comes from the data sets somewhere. Definitely take a read through this. Okay, so we have what are we looking at? I think this this text and label is defined by SST, and we're passing in this text and label as arguments for each of the fields that SST has. And so what we're saying is, okay, our text field, which we now see as torchText.data.field object, so this field object, it knows it's going to, when we eventually call this training data, is going to have to tokenize things based on the spacey tokenizer and lowercase everything too. And this label field is going to have to, convert everything to a long type. We then have the length of the training data, so 8,544. And looks like this is just the example of the first piece of training data in our training data. So the Rock is destined to be the 21st century's new Conan, and that he's going to make a splash even greater than Arnold Schwarzenegger. And we also see the label here, which is positive. Guys, I'm sorry, I should have told you to do this at the beginning of the lecture. I completely forgot, but we're going to need to download Glove. So what we're doing here is we're loading in pre-trained vectors. And if you remember what I spoke about yesterday, we can do this. We can download pre-trained word embeddings, and we can load them in. And this is what this vectors is going to do. We're going to specify, okay, we want to build our vocabulary. So remember what our vocabulary is, just a list of unique tokens. But we want to have the embeddings of these tokens to be initialized with the Glove embeddings. So we're gonna build this, and if we don't have this downloaded, it's going to download on our system, and I think it'll be placed. Oh no, I'm disconnected.
Do you have Ethernet?
Nah, bro. My back live. Okay, let me just answer these questions. Is Andrea's class in addition to the NLP classes over the weekend? No, it's not part of the NLP course. But he actually emailed me saying, oh, it'll be cool to see how we could use torch text in, you know, an industrial setting, something which isn't with one of these data sets that I just showed you guys here. So he put together a tutorial showing us how we can actually, you know, load in our own custom data and go from our raw data into something which we can have in a torch text object. So definitely going to be some cool stuff. I'll send out an email about that tomorrow on Monday, but that's going to be at 6 o'clock on Monday, I believe. Can't find model EN, doesn't seem to be a shortcut. Okay, so you need to download the Spacey language model. If you visit the repo, which I linked earlier on, here, so you'll see that we have this as admin run the following command. So if you're on Windows, just open up like a terminal, PowerShell, command prompt, whatever, and run run it as admin, and then, you know, run this Python M spacey download en. Or if you're on a Unix-based system, sudo, and then sudo run this, you know, run the same command. Cool, so this will download Glove, and I believe it will place it here, vector cache, yeah. So it'll download the whole of Glove, which is 800 megabytes, I know it's quite big, but we're going to be working with this Glove 50-dimensional, which is, you know, the 50-dimension word embeddings. Obviously, the higher up we go to word embeddings, up to a certain point, we're going to have a higher performance, but, you know, this is more just to show how it works than maximizing performance. Okay, so then we're just going to print the most common words in our vocabulary, and most common tokens, I should say, not the most common words, because we can see here that the full stop is the most common token. A comma is also a very common token as well. Then we're gonna look at, okay, so just important thing, this dot vocab might come up quite a bit. Just important attribute to know about the data field, and we'll definitely be using it more. So just keep in mind what this vocab is, as in this vocab attribute. This STOI stands for string to int, and all we're doing here, we're just printing a dictionary which shows us the labels that we have and their associated numerical values. So positive is 0, negative is 1. And neutral is 2. Okay, we're just going to define our batch size as 64, and you know, we're probably going to be running on CPU because I'm not sure if my machine actually has a CUDA GPU on it. We're now going to introduce this thing called bucket iterator. And what bucket iterator is, or what bucket iterator will do, is it will return iterators for the data that we pass in. So here we're passing in train data, validation data, and test data in a tuple, and we're returning a train iterator, a validation iterator, and a test iterator. In the next code cell, I'll show you what these do. But the argument that we pass to the splits method of bucket iterator is obviously the data, the batch size, sort within batch, and device. And now what sort within batch does is it will sort the texts according to the size of the length of those texts, right? And it's kind of been shown in NLP that it's better if you start training your model with shorter, more understandable, and easier sentences, and then gradually build up to longer and more complicated sentences. So the sort within batch will allow us to sort, well, one bucket iterator returns batches which are of similar lengths, and the sort within batch will sort the sentences within the batch so they're in ascending order. And we're also going to have padding tokens. So remember, we looked at that we looked at how padding works and the functionality of padding here when we looked at this word embeddings example. So run that. Can you try running the command, the other command that we have on the repo? So pip install -r requirements.txt. So we have this requirements.txt file, which should have all the libraries and packages in there. So torch text is in there. So if you just run this command from the NLP folder, well, actually, yeah, from the NLP folder, because that's where requirements.txt is. This command here, it should install all the relevant packages, and then your torch text should load in. Okay, so here we're just going to start off by printing the train iterator, so you can see what happens if you just print this object. And then we're just going to do a for loop over the train iterator to show you actually how it should be used. So just printing this gives us a bucket iterator object, but that's not what we're going to do. We actually use this by looping over it. Okay, so every batch that we have in our train iterator, and every batch is going to be of batch size, right? You know, we can call this batch, and I'm just breaking here so we can just see what the first, you know, toy batch or demo batch is going to be. So each batch now consists of it's an object, so a batch object of size 64, because we have this batch size 64 here, and it's got two attributes in it: .text and .label. So let's okay, let's break this down a bit more. Okay, so the first thing I want you guys to notice is that demo batch.text, which is this .text, has a shape of sentence length times batch size, right? So what this means is it's sentence length down and batch size across. So we have 32, or we have a sentence length, or our 64 objects in our batch, right? That's this dimension here. So that's 64 across and 32 down. And our label is of size 64. So every object in our batch has one associated label with it, which is positive, negative, or neutral, right? So this is 64 times 1, which is the same as saying 64. As in when you're talking about times, not as like the mathematical times, but the matrix shape times. So what we're going to do is we're going to transpose this demo batch into something we're a bit more used to thinking about, and that is representing things as batch size times sequence length. Okay. So that's simply done by just, you know, using this transpose, and we see here. Okay, so our normal, you know, as with the iterator, we load it in as sequence length times batch size, but when we transpose it, we obviously have batch size times sequence length. So that's 64 down, because we have 64 objects in our batch, and 32 across because our sentence length is 32. And the example that I'm giving here is just printing the first 3 elements of the demo batch, right? So this is element 1, element 2, and element 3, and we can see that these have already been have already been indexed by bucket iterator, I believe, or and this is basically, we can use this as our the word to index dictionary that we looked at yesterday in the first lecture, rather. This comes we obtain this by using by using torch text and bucket iterator and datasets.splits, or the data fields, I should say. So each one of these is going to be 32 long, where each one of these indexes refers to a individual word. Okay, so this is a word, or a token, I should say. This is a token, this is a token, this is a token. So all of these are tokens to represent this one sequence. Similarly, all of these are tokens to represent this one sequence, and all of these are tokens to represent this one sequence. Sorry, that's this line here. Now we're just going to do the same for label. So we see that label is of size 64, and if we print the first three labels, we see that we get 110. So that means that this is our training data, right? So for our first pair, we have a class label of 1, which is negative. For our second pair, we have a class label of 1. So this pair, class label of 1, which means that this is a negative review. And our third pair, we have a class label of 0, which means that this is a positive review. And what I'm going to do, I'm just going to print like the word to index dictionary that we defined yesterday, and how we did that manually, but just by using this the data fields, right? So we look at text, which is our data field, .vocab.itos, which is int to string. Text.vocab.itos, and this should return us a so this is returning us a list of all the ints in our see vocab.stoi. Why was it we printed the other way around? So this will be a dictionary. Okay, here we go. So the string to int is what we want, sorry. So this is our word to index dictionary. So word to index, so string to int, that's my bad, guys. But you can see here that we just have a dictionary, and we have you know, the associated mapping with it. "32 is the longest sentence in our batch. There could be longer sentences in the dataset." And the label vector, could you clarify what you mean about that, please? So maybe I've cleared it up by talking through this part. Maybe I haven't. So if you could just clarify a bit, then I can explain. Okay, so what we're going to do is we're now going to build an RNN. This code, I'm going to run through it. I'm not going to have you guys fill anything in on this part here, but we're going to define some RNNs later on where I'll have you fill things in those. I'm going to walk you through this class. So we're going to use this RNN to classify these movie reviews as well. So we're actually going to use it. So we have our constructor, which is obviously the init function, and within it we define 3 layers: an embedding layer, and this is going to act as a lookup table to map our tokens into their vector. And we're doing this from pre-trained, right? So remember, we loaded in the vectors earlier on into our vocabulary. Now, after this code cell, we're not going to be looking at pre-training the vectors. We're just going to, you know, look at how we can use the embedding layer from scratch. But just for now, we're just loading in the pre-trained word vectors. So the embedding vector transforms the indices that we saw. So, you know, these as they come into our class into the word embeddings. Actually, this is 50 deep. And we're going to initialize our model with the pre-trained word embeddings. And during training, this layer is going to this is essentially just a normal PyTorch linear layer. So this functions the same way as nn.linear, which means that it's going to be initialized with these vector weights, but it's going to be fine-tuned during the training process. So the vector weights will be slightly modified based on you know, whatever loss signal we're sending back to our network. Secondly, we're going to define an RNN. And what we're going to do here is we're going to specify the batch dimension being first. So this just allows us to work with shapes that we're a bit more familiar with. And when we load in the data, we'll just transpose it all. And this will give us, this transpose shape of batch times sequence length. And then finally, a linear layer. So this linear layer receives the last hidden state of the RNN and outputs logits of output dim dimensionality. So if we go back to our diagram, this is the linear layer that we have. So it takes the last output state of the RNN, and then outputs logits, which we use, which we compute our loss against to make predictions. And that is here. Okay, so just to talk about this RNN for a second more. We have a bidirectional flag, so ignore this for now. We'll come back to this class in a second when I talk about bidirectionality. But we just have this for now, which will be false for now, so we don't need to consider that. And I want you guys to know that RNNs can be stacked, and that just means that we can have multiple layers in an RNN. All we're going to be doing is looking at the one layer case right now, and this will keep things nice and simple. So as I mentioned, this last linear layer, it takes the final hidden state and feeds it through a fully connected layer. The dimensionality for the output is as normal, equal to the number of unique classes that we have in our output. So the number of unique classes in our output is obviously the number of unique numbers that we have in label, which is 3, right? These are our labels, 0, 1, and 2. And then we have something called dropout. So dropout, I don't think is a concept that we've introduced in our deep learning workshop series. But what this does is it sets a random set of activations in a layer to 0. And this prevents the network from learning to rely on specific weights during training, and it also works as a regularization technique to prevent overfitting. And we only use the dropout layer during training and not during test time. So essentially, every time we call dropout, it's just going to say, here are the neurons that we have in our network, at the layer that we want to call it on. And we just want to zero out some of these neurons, so the network has to learn representations from, not seeing everything, but seeing a partial representation of what our representation should be. And these, neurons that it drops out are going to be randomized at every forward pass. So we can hope that our network can construct the same output by, not relying on all the neurons, but just like a subset of them. And hopefully this leads to some stronger representation of our data. So, let's see, we got questions. Yes, I am recording this. What if we don't want to fine-tune the layer? That's a good question, especially if we're loading in pre-trained vectors. So I think there is an option called requires grad. PyTorch. Which we can pass in. Or what we can say is for param in self.embedding. So this embedding has a or all the linear layers. If you loop over them, we have it's dot parameters has this function called parameters, and we can call it. Can't remember if I think it is a function. So we can call it, and then it returns us an iterable, and we can just say param.requiresGrad equals false, I believe. And this means that we're not going to be fine-tuning our word embeddings. But just note that this isn't unique to word embeddings. So if we had like self dot layer 1 equals nn dot linear input size output size, this also has a parameters object function method rather. So we can say for param in self dot layer 1 param.requires grad equals false. And that stops us fine-tuning during training. Yeah, so I have this comment here saying that we can also initialize the embeddings from scratch. Instead of passing in pre-trained, what we do is we pass in input size, which is going to be our vocabulary size, and are embedding the dimensions that we want our embeddings to be. So in this case, it'll be 50, right? So we'd pass in vocab size as the example, and we can do that just by, so vocab size equals text dot or the length of text.vocab. So this is the number of unique tokens in our vocabulary, or just the number of unique tokens is the length of our vocabulary, and embedding dim, which would be 50 or 100 or whatever you want it to be. Yes, I am recording this. Tensor. So tensor is the data structure that we use to store our data, basically, and it is basically analogous to an array. So you can think of it as an array, right? So it has a shape, and typically what we're doing when we're working with NLP data is we'll be working with rank 3 tensors, and this means that this is a rank 3 tensor that we see right here, right? So a rank 3 tensor means that it has three kind of I want to say dimensions, but it's not a dimension. It's just it encodes three. What would you describe a tensor as?
A tensor.
Yeah.
A matrix, but with more axes. It's got
Yeah,
more axes.
it's like a multi-dimensional array, right?
Yeah.
Yeah. What would you define rank as? Or what's like the distinction between rank and dimension?
Yeah.
Okay. So rank just means if we were to do print the length of our shape, right? So every layer has a shape object. So for example, the shape of this embedding layer is going to be vocab size times embedding dim. Actually, it's going to be batch size times vocab size times embedding dim, but the PyTorch module doesn't include the batch when we define the arguments, because it just assumes all batches are going to be the same size. So let's say we had so shape embedding layer is equal to batch size times vocab size times embedding dim. Okay, so a rank 3 tensor means that it has 3 of these elements, is the length of this list, right? So the length of this list is 3, which means its rank is 3. But the shape is this, right? The shape is batch size times vocab size times embedding dim. And let's look at that here, right? So here we have 3 different sentences, which means our batch size is going to be 3, right? So batch size, each one of these sentences. Our we're not looking at the embedding layer here, but our sequence length, so how many items we have in our sequence, is going to be 10, because we have 10 items in each sequence. So that's going down, and going across is going to be our dimensions, which in this case is embedding dim. So this will be 50 in this case, and 10,000 in this one hot case that we looked at. And a tensor is essentially the data structure that we use to store that object. Okay, and why do we have... Okay, so let's look at our RNN. Our RNN takes in as input embedding size, right? So this is self.embedding. So first we embed our inputs and then we pass it into our RNN. And that means that this is going to take... the input size to our RNN is embedding size. Then we have hidden dim, which is the dimensionality that each word is then going to be output as, right? So our input is going to be the embedding size of each token, right? So remember, these are going to be passed through an embedding layer first, and then we want to pass the embedding into our RNN cell. So we embed this input into embedding size, which is why the input to our RNN is embedding dim, and we output a hidden state vector, right? So for every time step, we have a hidden state vector. So the output of the RNN is going to be hidden dim size. Yeah, we take in as input to an RNN the previous hidden state as well, but this shape stuff is managed automatically for this previous hidden dimension. It's managed automatically for us by the RNN module, so we don't need to worry about it. So we only need to define like what our embedding size is and what we want our hidden dimension size to be. So when we get to this linear layer, we have linear layer hidden in, which, because we're not looking at the bidirectional case right now, is the hidden dim. So is of size hidden dim, right? So we use this is our linear layer, and all it takes is the hidden dim. It doesn't take in the last output either. It just takes in the hidden state, I should say. And obviously the hidden state is just of size hidden dimensions, which is why we don't have in our RNN we don't take in hidden dim plus embedding size. We only take in hidden dim. Okay, so let's run through the forward method of this. So our RNN is going to take in some text, and here I'm going to introduce some acronyms, just to, one, clear this up a bit, and two, when you guys start reading papers and more mathematical things, you're going to see acronyms which are going to be used, which represent and this is kind of to get you used to more the terminology that you'll see in like a machine learning environment. So B is going to be our batch size. T is going to be the length of our maximum sequence. So remember, in this example here, T is 10 because that's the length of our sequence. E is going to be the embedding dimension. So how many dimensions we want to basically represent each word by. D is going to be our hidden dimension, so that is the size of this of each of these hidden states. And O is going to be the output dimension, which is the unique, feature, or it's going to be 3 in this case, right? Because we have a label which has it can only take on one of 3 values, so our output dim is going to be 3. So the shape of the text that we feed in is going to be B times T. Now I'm just going to use B's and T's moving forward from now on, and I understand that could be a bit uncomfortable at first, but I want you guys to refer back to this acronym dictionary, I guess, glossary, whatever, and understand what I mean when I say B and T and E and D and O. So the first thing we're going to do is we're going to embed our text. Okay, so this is going to return us something which is B times T times E. So we've got our sequence length, which we've fed in. So these are going to be, these. So this is a batch size of 3 times 32, but we're feeding in batch size of 64. So we'll have like a 64 by 32 coming in. So 64 will be this B, and 32 will be this T, because 32 is the sequence length. And then we embed these. Okay, so this is what the embedding layer does, and what this will do is it will embed our inputs. So it will turn these numerical indices for where the word appears in our vocabulary into a word embedding, which is obviously what we looked at in the previous lecture. So that's where this 3D shape now comes from. We now have something after we've embedded it, which is B times T times E. And then we run dropout. So as I mentioned previously, this is essentially equivalent to saying some of these words are now going to be non-existent on this forward pass in the model, just a random subset of these words based on the dropout probability. So the dropout probability is something that we pass in. let's say it's a half, for example, just to keep the example easy. So that just means that half of our words are going to be zeroed out after running this dropout. Just a random, uniformly random selection of a half of half the words. Okay, and then this embedded object of b times t times e is what we pass into our RNN. And an RNN in PyTorch returns two values. The first thing it returns is all the hidden states of the last RNN layer. And the second thing it returns, well, I should just say the hidden state of the last RNN layer. I'll keep it as all because when we look at bidirectionality, yeah, this is going to be a bit clearer. And secondly, it's going to return the hidden state of the last time step for every layer. So this is going to be of batch times t times d, where d is obviously the hidden dimension. So what this means is that if we look at this first image, for every time step, we can collect a HT, right? So this HT exists in this diagram, which is here. So we have track of all of these, and the first thing that our RNN returns is going to be a tensor which contains all of these values, all of the hidden states of our RNN. So that's where t comes from. So from every t, we're going to have something of d dimensions, right? So for every time step, so for every word that we're parsing through our RNN, we're going to have a hidden state which is d dimensions. And it also returns the last hidden state for every layer. We're just looking at the number of layers as 1 in this case. So we just have a tensor which is returned to us, which is going to be in this particular use case with unidirectionality in one layer, 1 times b times d. Okay, so b is batch size and d is the hidden dimensions. So it's just saying that we have the last hidden state of d dimensions for every item in our batch when the number of layers is 1. But you can see how when the number of layers is 2, we'll have the last hidden state for every time step in our batch per layer. Okay, so this is essentially b times d. So we have batch going down and hidden state going across. What we're going to do is we're only going to consider this last hidden state right now because that's what we're going to base our classification off. We're going to say, okay, I want you to classify this mover review based on this hidden state here, which incorporates all the previous information that we've seen in our RNN. So we just want to use the last hidden state, and we pass. We're going to squeeze it, and this is just going to remove that 1 that we have here. So we just have this batch times d, and then we're going to feed it into our fully connected layer and run dropout. Okay, when can we take a break and run dropout? Okay, yeah, let's take a break now. We'll take a maybe 5-minute break because we're not doing any code, but you know, feel free to check out the groups option. Feel free to ask questions, and I'll be around and I'll be interacting. Might come back on live to answer some questions if we got some good ones going. I want you guys to, if you do go into groups, and definitely please go into groups and discuss with the other colleagues. We seem to have quite an interactive chat today, which is really nice to see. And try and discuss why we're using dropout here on the output of embedding, but why we're doing dropout here as the input to self.fc. So this is the question that I want you guys to answer. Okay, so we're going to return at 14:11 is what I'm going to put the timer to. See the cool questions. Yeah, sorry, when I zoom down, because I zoom at an angle, sometimes it zooms in and out. There's a good size of zoom, which I think is this. If I zoom in any further, it kind of ruins the text, and I have to horizontally scroll across. But if this is a bit clearer, I'll keep it like this for now. Okay, see you guys in a bit. Yo, guys, welcome back. Welcome back. I read this answer, gave it a little upvote, as you can see, because this is absolutely correct. I'll just explain it a bit more. Okay, so whoever responded with this, thank you very much. And what they've said is for the first time we see dropout. So here we're applying dropout on the logits of the embedding. So we're applying it. So this returns something, and we're applying dropout on top of that. Okay. And then in the second case, where we have dropout last hidden, we apply dropout on the representations before converting it, before passing it through the fully connected layer, right? So this is saying run dropout on these hidden states, and then do the fully connected layer on the dropped out version. If we had dropout on the outside of here, it would say run this fully connected layer on the hidden states, and then our logits will have some of those values dropped out, and that's not what we want, because we need our last fully connected layer to be, intact, because this is what we're going to run our softmax over in this particular case. So to kind of show you guys dropout visually, hopefully if I just search in dropout, never done this before, but oh, cool. I like Google's coming up with good search results lately. Okay, I guess this example here, sure. So this is just like your normal feed forward neural network. And with dropout, we're saying don't consider some neurons, right? So in one pass, so forget these two layers here. So we've applied dropout to the inputs first of all, and then to the second layer here. So just for an arbitrary layer, for this layer we have all these inputs, all these neurons sending their values to all the other neurons. When dropout occurs, we essentially kill one neuron per pass, right? So we're saying, okay, we don't want this neuron to have any outputs. So we just so we just look at the next neuron. Is it dropped out? No, this one isn't. So we just have the outputs coming out of it. Okay, and we don't want to do this basically here, right? So this is only one class. Don't know if there's like a multi-class example. This is probably a better way of representing it. We don't want to apply we don't want to apply dropout to the output or to the values in these neurons, because these values are what we're going to compute our loss against. So this example here, where we've dropped out this neuron and this neuron, this is what we're doing here, right? So this is saying that, okay, so over the penultimate layer, the last hidden layer, apply dropout. I hope that clears things up. Okay, so we run this class. Nope. So that was a bit of a meaty class. I'm glad we managed to get through that, and I hope you guys understand. It's kind of going to set the basis of everything moving forward. So if you guys don't understand any code in here, then please let me know. And we're just going to initialize some of our parameters now. So the input dimension is going to be the length of our vocabulary, and our embedding dimension is going to be 50. We're using the glove embeddings, so makes sense. We're going to define our hidden dimension as 128. This is a pretty small value in terms of today's NLP systems. You'll usually see like 512 being floated around a bit more now, and 1024 for the big models out there, even bigger for the giant models out there. We have our output dimensions, which is just going to be the length of the vocabulary of our label, which is obviously just going to be 3. And for now, we're setting the bidirectional flag to false. We're having our dropout be set to 0.3, and we also pass in this thing called the pad IDX. So the pad IDX is just saying, okay, what is the pad token? And when the pad token is seen in this embedding layer, it's just going to initialize the embedding to 0. Sorry, and I just wanted to focus on on this here for a second, because whoever answered this question, you're using embedding in the wrong context. Embedding specifically only refers to the embeddings of words. Okay, so embeddings are after we feed this word into our embedding layer, what we get is a word embedding. It's not correct to use the word embedding in really any other context with NLP. So we can use the word representation instead, and an embedding is a representation of the word, and every other hidden state that we have, we can call it some kind of representation because it is a representation. So if you just replace the words embeddings here with representations, then yeah, you've got the right terminology. And it's not converting it into a fully connected neural network. It's running it through a fully connected layer. This is a good question. How does the connectivity of RNNs get affected by dropout? So dropout, I believe, is only applied to the final dimension. So we're still gonna, if we think about this in just terms of t times e, so we have the embedding and then we apply dropout. So it's just gonna zero out some of the t's basically, right? So all of the embedding values for the t that it has decided to drop out would be 0. If you can clarify what you mean by the connectivity of it, whether you mean like where did this tab go? If you mean like within these from this input to this output, and if the relation of the dropout is the same across all the inputs, or if if we drop out on this hidden state, for example. If you could just clarify a bit, then that'd be quite useful for me to fully answer that question. It's a really good question, yeah, but just want to kind of get to the point of which you're unsure about. Okay, so just run this and we'll initialize our RNN. Just want to talk about evaluation. So there's this section and just another brief section on it. So, the natural choice of evaluating things is accuracy. The percentage of all examples that our model has labeled correctly. However, this is okay for balanced data sets, but for unbalanced data sets, it's not really viable. So we can imagine a case which has lots of positive examples and a very few negative examples. So a bad classifier can actually just assign, if just by taking these numbers here, if it says everything is going to be positive, then actually our classifier is going to have like an accuracy of 99%, right? Because it's only got these 100 examples wrong. But this isn't really a good indication of evaluation, because ideally it's better to have these 100 examples right, because we want to learn what makes an example negative, not just classify it. Well, we want ideally our network learns what's making this data point into a negative example. So even though we get 99.9% accuracy, we haven't really learned anything, because it's just predicting positive over the 1 million examples. So there are other useful metrics such as precision, recall, and F measure. And I'd direct you to the Wikipedia pages to get a bit more information about these, because I think they do a lot better job of explaining it than these one sentences here. And they also have visual representations. For now, we're just going to use accuracy though, just because we don't really have too unbalanced of a data set. But it's really important that you guys know about precision and recall in particular. So our accuracy definition function is just going to take in our predictions and the ground truths, run softmax over it, and get the maximum value of this softmax. We can just do actually preds.max. So this would be the same as doing preds.max, because our softmax is obviously going to keep the same the highest output before softmax, and post softmax is obviously still going to be the same index. Then we just compare whether the predictions are equal to the ground truth and convert it to float for division, and then we divide the two to return the accuracy. I still see it live. If other people comment that the video is frozen, I can try do it, but can you refresh if it's still frozen? Since all, by connectivity I mean it's all the inputs are connected. So all of the inputs come into our RNN class as B times T, right? So when we apply dropout, we're applying it over all the batches for you know, and we're applying the dropout on certain time steps which are deemed which are randomly chosen by this dropout method. We can actually pass dropout into this RNN class. So actually, there's a dropout flag here. I think it's just dropout, and I'm just gonna remove this for now, but we can do that. And what that would do is it would drop out, you know, every hidden state calculation. It will probably drop out some of the elements in that hidden state. Okay, cool. So we'll just we want to optimize. We have a multi-class problem, which is why we're going to use cross entropy, and we're going to use Adam to optimize our parameters. So it's just a train loop, a pretty straightforward train loop. Okay, so we should obviously start all of our train loops with model.train. And it's just good practice, even if we don't ever use evaluation mode. So there's model.train and model.eval. And what model.eval does is it will turn off dropout. So we don't want to have dropout on during our evaluation stage. We only want it on during training. But when we actually come around to evaluating, we want our network to see all the outputs there. And it will also turn off something called batch normalization. We'll look at this more in our last lecture, so don't worry about it too much for now. But it's just good practice to have this dot train there. Okay, now we're gonna iterate over loop over our train iterator in batch. Okay, so remember that batch contains a .text attribute and a .label attribute. So after zeroing out the gradients, we're just going to say, okay, text equals batch.text and label equals batch.label. Now, this is loaded in as sequence length times batch size, or T times B. But we want to reshape this to B times T, just so we can think about, we can have consistency when we're talking about our shapes. So we're just going to transpose this, which is what this .t does, okay? So this .t stands for transpose. And that will flip the axes, so this will just be B times T instead of T times B. Then we feed our text into our model, so this is the forward pass of our model here, and get some predictions. We're then going to compute the loss and the accuracy, and then we're going to backprop and then perform gradient descent. These are just to show the losses and the accuracy per epoch. And our evaluate function works kind of similar. So here we turn on the eval mode, so that deactivates dropout and batch normalization. And we don't want to compute gradient, so it's also good practice to have this with torch.noGrad. So under this function, we're going to loop over our iterator, and we're going to use this both for our validation set and our test set. But if it just helps you think of it, just think of this iterator being our test iterator. Okay, so for every batch in our test iterator, let's get the text and the labels for it, transpose the text. So that's the same thing as we did here. So this part. and feed it through our model, work out the predictions, calculate the loss, especially relevant during the validation stage, and the accuracy. Now we're going to train our model. Did I run this code cell? Yes. Accuracy is not defined. I wonder if this will be able to train. Okay, so we can see each epoch taking about 4 seconds to complete, and we should see our train accuracy increase over this time, up to a certain point actually. So just going to keep that training for 15 epochs, and we should see like some slight increase in our accuracy and a loss, especially in our a decrease in loss, especially when it comes to our training. Oh, loss.item is essentially the value of the loss. Item just gives us the loss object is a tensor, but the item is just like the numerical value of the loss. Yeah, you're expecting something along those lines. So I don't imagine this will get too high. Mine's on around 55%. But you can see like the training loss goes down over time. So it starts at like obviously 1 point something and it finishes at like 0.59. Yeah, there's a slight increase, but that's kind of is stochastic. So okay, I guess this part isn't stochastic, but we do see fluctuations in our loss, and if we carried on training this, we'd eventually see this go down to 0. That'd be overfitting though. We can also see our train accuracy has increased up to a certain point. I saw somebody put in saying that they have 59, which is pretty high. So cool. You got some nice random initializations there. Mine seems to plateau at about the 55%. Yeah, this is probably chance. What is our model trying to predict? So our predictions are going to be 0, 1, or 2, where 0 refers to the movie review being positive, 1 refers to the movie review being negative, and 2 refers to the movie review being neutral. So this is what our model is trying to predict. So our output dim is going to be 3, because we have those 3 classes. We'll just evaluate our test loss, and we see that, okay, we actually get a pretty decent test loss of test accuracy of 58%, 59%, which is pretty decent. Okay, so I'm going to talk about bidirectional RNNs. Actually, what I want you guys to do is I want you guys to take 10 minutes. No, not 10 minutes. Maybe 7 minutes. Read through this and fill in these code cells. Go into groups, please. Try and get an understanding for why this diagram is the way it is, what this text is saying, and see if you can call it on with the bidirectionality flag, and understand by reading the comments in this code cell what's going on. And guys, please go into groups. Please discuss this with other people, because it will definitely help solidify your understanding of it. So I'm going to return us at 39 past. Yeah, dropout just tends to be a fixed value. You can vary it per layer, but it's a hyperparameter, so there's no like solid answer of what the best dropout is. That's actually a good idea whether people optimize the proportion of dropout as well as the function of the performance. I don't think that's true because I don't think it's easily doable to do that. I don't think there's much point in doing that either. So we initialize the dropout probability in our constructor. So during every forward pass, we're not redefining this probability. But the idea is that the higher dropout that we can get without seeing a loss in accuracy, and actually up to a certain point, dropout increases accuracy as opposing to decrease it. But there comes a threshold where if you drop out too much, the model doesn't have enough information to make its prediction. So you kind of have to learn it on a per architecture basis how much dropout you want to use in between each of the layers. And obviously you can have different dropouts in between different layers, right? So I can have a dropout 1, which could be between the first and the second layer, and a dropout 2, which could be between the second and third layer, but with a different dropout probability. Yo guys, we're back. We're back. We're back. All right. Um. Guys, can you post these two lines? They're relatively straightforward. The important part was understanding what was going on in the RNN class when we have a bidirectional RNN. Okay, so when we're facing problems where all time steps of the input sequence are available, bidirectional RNNs train two RNNs instead of one RNN. And this is, so they do this by having one RNN trained in the forward time direction. Okay, so this is just this is exactly the same as what we've looked at, right? So this is the forward time direction. We're moving forward in time. We're going from the start to the end. And this is, we're moving forward in time, so this is where the arrows are pointing. This is the forward time direction. Bidirectional RNNs are two RNNs, right? So think of them as two separate RNNs. One which goes forward in time, and the other which goes backwards in time. So this backwards RNN reads things in reverse time order. So it starts with witty, and it builds up a representation for the whole sequence based on going backwards. And this basically allows us to augment our representation. So just a quick example. So imagine that you see on the left context, we went to, and obviously this context is very general and a lot of different words can be put in this ... So, London, cinema, whatever. It could also be support, so it could be a verb instead of a noun. And kind of just by seeing these, it's hard to predict what the next word could be. But if we see things from both directions, so say that this word is blanked out, but we have access to the things moving forward and the things moving backwards, we can understand what this word is meant to be because we have access to the backwards information as well, right? I think the accuracy on these should stay about the same, so we should be looking at something which is about 50% or something, 50 to 60%. And I'll talk about how we can improve this in a second, but this is just a general architecture which should allow us to improve this information. So our bidirectional model is going to be, guys, can you fill this in? Can you help me out, please? So I want you to note that we take the final output from the forward RNN state. So this arrow indicates forward. So this forward HT incorporates information from all the previous words, and this backwards H0 incorporates all the information from the forward words, right? So here we start with witty and we move backwards until we get to this. And then the hidden state, which we use to pass into our softmax, is just going to be the concatenation of this final HT and this forward HT and this backwards H0. Yeah. Okay, yeah, so basically it's exactly the same. We pass in the bidirectional flag, but we're going to pass it in with true. And we train the model in the same way. So we had train here, and now we're just going to, in here, we're going to call train, but instead of model, we pass in bidirectional model. So we'll see that when we train this, it should take about twice the amount of time to train, because obviously we're running two RNNs and not one RNN. Okay, so let's talk about what we're doing in the code. Okay, so we're assigning self.bidirectional to bidirectional. So remember, this is just a flag, whether it's true or false. In our RNN, we say, okay, bidirectional is going to be bidirectional. In this case, it's true. And if we have a bidirectional RNN, our hidden size to our output layer is going to be twice the hidden dimensions. And the reason for this is that we have this concatenation up here, yeah? So this HT is going to be of hidden size, and this H0 is also going to be of hidden size. So when we concatenate the two together, we have the hidden size plus the hidden size. So that's 2 times the hidden size. And this HT that we feed into this linear layer is going to be 2 times the hidden size because of the concatenation. So when we have a bidirectional RNN, the shape of all hidden changes from D to D times the number of directions that we have, right? So this is either 1 or 2. So now the shape of all hidden is going to be batch times time times 2 times the dimensionality. And what we want to do is we want to concatenate the final forward hidden state and the initial backwards hidden state as our last hidden layer. Actually, wonder if we can do this more efficiently. So we should just be able to say that okay, no, I'll tell you why we do it this way. Okay, so we take this last hidden, which is this. So we're not working with all hidden, we're working with last hidden. And remember, last hidden is num layers times num directions, and num directions in this case is 2 because we're working with a bidirectional RNN. So we have something which is 2 times batch size times D. Okay, so we take the first element from this tensor, which is going to be 0, obviously, and this is going to be our forward direction. So we want to return all the elements from our forward direction, all the last hidden time steps for the forward direction, which is what this is saying. So this is going to return something which is 1 times B times D, and from the second index, which this 1 refers to our backwards, we want to take all the B's and the D's from this first index. Okay, so just to, obviously this is under a different context, but just to kind of clarify what we're doing, we have, instead of 3 we have 2, right? So let's just consider this green and this blue one. We want to take this first one and we want to take the second one and we want to concatenate the last hidden states of them together, right? So what we're really doing is we're saying, okay, we have access to this this vector, which is going to be the last hidden state. So we want to concatenate the last hidden states of the forward direction and the first hidden state of the backwards direction. Or in this case, the way PyTorch implements it will be the last hidden state of the backwards direction, which is actually in our diagram the first hidden state. I know that's a bit confusing, but reading the documentation will definitely clear that up for you guys. And I will link that now in case anybody does have a does want to take a bit more of a further read of that. Okay, here we go. So link this because the docs take quite long to load. If you just read the RNN class of this, we'll see bidirectional, and we can look at the output shapes to show us, or I guess this is what we want, HN, which is the last hidden state, to show us how these directions are represented. Okay, so we're going to concatenate these two together across the last dimension, which is represented as -1. So this -1 just is used to refer to the last dimension. And that's in we're in this part of the if flag, and then we just run it through our fully connected layer like we did before and return the logits. Okay, so for some reason I'm seeing something which is significantly worse. To the guys who answered that earlier on when they were saying worse accuracy, were you seeing something that was this bad? Just a bit curious actually. But you can see that the time it took to run per epoch is basically double because we're running 2 RNNs. Okay, and we can run our test, and obviously this should be a bit lower because for some reason our RNN is predicting worse. I just want to know if that's an issue on my end with something I might have changed, or if everybody was getting like that kind of discrepancy. I don't think it's got anything to do with the optimizer parameters because this train loop, it might do. Yeah, okay, you're completely right. Whoever pointed that out, yep, thank you very much. That's a really good catch, and I'll move it into our train loop. So I'll just leave this train, and hopefully when we come back to it, we'll see something higher. Thank you. So with PyTorch, when you run it on GPU, you have to declare all the inputs as coming in from GPU as well. So perhaps this is something that should have been done, but here we should just do .to device. So for each of the not the labels but the input. And actually I'm going to put this to .to device as well because I'm unsure whether the loss function will be computed on the GPU or CPU. So if we just put in to device here, then that should sort out your issue that you're getting for the GPU. Okay, so we're going to look at language modeling now. And kind of everything that we've done, including this word-to-vec algorithm we implemented in the last lecture, and this RNN that we've done, and this bidirectional RNN that we've done, they all fall under the subset of language modeling, because by definition, a language model is just a model which can represent language. So a language model is required to represent the text of to make this text understandable from the machine point of view. And it's kind of the core part of NLP and the base of all NLP tasks, because we need to have a model in this, for example, this model which understands language. By the way, whoever did tell me about the optimization parameters, thank you very much. It looks like that did work, and we can see our accuracy being very slightly higher. We can't call this, this could just be because of a random initialization. But this bidirectional RNN wasn't meant to significantly outperform the unidirectional one in this context, and we'll look at where they're actually super useful in a bit. Okay, so language is essentially a sequence of characters or letters which build into words, which build into sentences, and which build into paragraphs. And when we comprehend and produce spoken language, we're kind of processing these continuous input streams of undefined length. And that's even the case when we're dealing with text when we read it normally, right? Like, words can vary with the amount of characters in them, sentences can vary with the amount of words in them, paragraphs with the amount of sentences in them, documents with the amount of paragraphs in them, and so forth. It's not like a fixed number of words per sentence. And an RNN is actually a perfect fit to model language data, because we can represent languages of any sequence into a fixed length vector, right? So we can represent a sentence into a fixed length vector. And the difference between like word embeddings, which can be thought of as some kind of language model, is that word embeddings don't take into account word order, whereas language models do take into account this context. And if you don't take into account word order, the representations of the sentences aren't going to be the same. So it was really not good, on the opposite quite bad. And it was really not bad, on the opposite quite good. Even though the words are the same, the meaning of these two sentences are different. So kind of what we want to do with a language model is this many-to-many task up here. And we can also do it in the one-to-many task as well. It is more suitably framed to this many-to-many task. So the way we do it is we have an input, and our input is going to be this special start of sequence token. Yeah, sorry, I'll just clarify the optimization thing. So what I did was I moved it from outside of the train loop to inside of the train loop. So anytime we call the train loop with the model that we're passing in, it's going to initialize the parameters to that model. And the dot device should be added to where we load the data. So batch.text.toDevice, and when we initialize the model as well, so this one I forgot to add, we should also put in .toDevice. And this will have everything running on the device which was specified by a conditional if statement, which was put somewhere up at the top. You'll need to do the same for evaluate as well, so these should be .toDevice. I'll make sure this is fixed for the next time we run the session, so thank you for pointing that out. Okay, so I'm going to introduce a new term here called autoregressive. And RNNs are autoregressive because they take into account they use the previous outputs of the model as in to influence the next inputs. Okay, so I'm going to walk you through this diagram. So we have an RNN here, which is unrolled through time, which is represented by these orange boxes. So this is the same as this, right? So we have an RNN which is unrolled through time, and this means we're just showing each of the cells individually as per time component. So we have this special start of sequence tag, which we feed into the model, and the model outputs a prediction of a word. Okay, so here we output our y hat is AI and our ground truth is AI. Okay, so we just output a prediction of a word, and then at the next, this is during the training process, by the way, at the next time step we use this paradigm called teacher forcing. And what teacher forcing does is this next input word is going to be the output word of the previous RNN step. Okay, so here we might expect x1 because the output of the RNN is this y hat 0 to be AI. But teacher forcing means that we use the ground truth instead of the predictions. But when we compute the loss, we use the outputs of the RNN to compute the loss against. But we feed but for the next time step we feed in the ground truth token of what we're expecting the word to be. So here we have start of sequence, and we feed it in, and the first token produced is AI, and this AI gets sent to the next time step. So it gets sent to be the next input of the RNN, obviously along with the hidden state, and then our network predicts researchers. So y hat 1 is researchers, but the ground truth is core. So we use we use teacher forcing to say, okay, even though the network outputted researchers, we want to feed in core. So we want to feed in the previous time steps output, the ground truth of the previous time steps output. So this is y0 for x1, that's y0. For x2, that's y1, and for xt, this will be yt minus 1. So we want to feed this into our network and make predictions, right? So here we see that our network has correctly predicted has, and we just continue this to the end where we predict the end of sequence token. And to do this, we kind of have our data be our labeled data as well, okay? So what we're going to do now is we're moving away from this sentiment classification task, and we're going to be looking at a language modeling task. So we'll declare our we'll start our torch text process in the same way by declaring a data field, and this time we're going to tokenize with spacey, and we're going to say that the very first token is going to be start of sequence. We can also pass in lower or equals true here to lowercase everything, but we're not going to do that for now. There's no particular reason for that, but we're just not going to do it. But we can do it if you wanted to do it. So you guys feel free to add lower equals true if you wanted to lowercase everything. And we're going to be using the Wikitext2 corpus, which is a popular language modeling dataset. There's a bigger one called Wikitext 103, which I think is 103 million words, but this is just 2 million words, which is where the 2 comes from. So this is just a language modeling dataset, and it's a collection of the texts from good and featured articles on Wikipedia, and we just load it in the same way that we did with the SST. So wikitext2.splits of text. Here we're going to be using 100-dimensional glove vectors, and we're just going to print some very, very basic statistics of it. I'm connected. Yay, I'm offline.
Oh, okay.
Yeah, you get the same.
You need an Ethernet.
My laptop don't have an Ethernet port.
Sure.
Oh wait, maybe I've got one in
Converter.
I think I have a thing which might have an Ethernet port.
Where you at, Haroon?
No?
Where are you at?
I'm trying to go. I'm just exploring it.
Cool.
Got no internet there.
Sorry.
I've got no internet there. So it's good.
You want to see to
I mean, I think it's more important that he gets it when it comes in.
that? Is he cut out?
Yeah. I'll just do I'll use my fixed Wi-Fi.
Right, I do have an Ethernet.
Script.
Haroon, my legs are fucking dead. Honestly, like my hamstrings.
Wow, yeah. I mean, you did some Matt Jones stuff.
Yeah. Oh.
Plus the double backflip, you know what I'm saying?
You did a double backflip.
Yeah, we can call it a double backflip.
It's a double
I think we're on stream, so everybody knows that Harry did a double backflip.
No, I did 2 in a row immediately after each other. It wasn't a double.
Oh yeah, not.
So,
I guess yeah. It's like it's what's it called in football? You know when you don't hit it off the volley, where it's like one bounce and then you hit it.
Yeah.
It's like you took one step and then you jumped. I guess.
Successful backflip.
Oh, it's called a half
volley,
It's
right?
called a
Yeah.
half volley.
Yeah.
So that's a half double backflip. Okay, a single flip.
Okay.
Yeah, I mean that's a good distinction.
Cool. Sorry about that, guys.
Half double backflip.
I'm gonna continue from where I think I dropped off, but if I've missed anything, then just feel free to leave a comment, and I will obviously return to that point back in time. No file or directory. Interesting. Right, so we have a wiki text too. Just might need to delete this folder. Run this again. Cool. So we're downloading Wikitext 2. And we obviously downloaded Glove earlier on.
Why is the image on the website, bro?
So we want to work out loss compared to. This is a really good question, by the way. Not something that I covered, so I'm gonna give you a little upvote for that. We want to work out the loss compared to the sequence that we're currently trying to predict, right? So at train time, we'll have a sentence. So in this case, this sentence is represented as the Y's. So AI core has blah blah blah. This is the sentence that we're going to work out the loss over. So what's the question? Why we still use the core input text? So we use we can set this as a ratio, right? So we can say 100% of the time use the ground truth to make predictions, or we could also say like half the time 100% of the time use the ground truth as the input to the next time step. Or we could have it as a ratio, so we could say half the time use the ground truth and the other half of the time use the network's predictions. And these are just different learning strategies that we could use. It's been shown that teacher forcing works well, which is why we employ this technique, especially when it comes to translation, because it kind of forces the network to learn what the correct word should have been and to learn to generate the new correct token based on the word that it has previously seen. Or the words it has previously seen, I should say. Okay, so what are we printing here? Okay, so we see that our fields is just text. That's the only field that the Wikitext 2 provides, and the length of this is obviously 1 because we're just it's just one long giant string. So what we've essentially done is if we print text right now, we have printed one giant long string, which is just 2 million words from Wikipedia in one string. And we're going to use and the total number of unique tokens is 33,000. We're going to use something called BPTT iterator, which allows us to define a length to say, okay, well, actually, we just want our language model to have everything to be this BPTT length, which in this case is 30. Okay, so we're going to create 3 iterators again, similar to what we did last time, just train data, valid data, and test data. And that comes from here. And obviously define our batch size and the length that we want each of our sequences to be. We'll just print one to show you what it looks like. Obviously these have all been mapped to their relevant index, so we could just say We could use like a text dot vocab dot itos, and then say, okay, so we want to have a list, so print int string for let's do the other way around. Okay, for sequence batch in demo batch.text, print sequence print batch. Interesting. Oh, right, sorry, because it's different dimensions, so for sequence, so I'm going to do this the other way around. For batch in text.t, so here we see that we're printing our sequences. Not quite right, but the point is, what I want to say is that we can just do text dot vocab dot string to int and pass this in, and now we should see words, which we don't, into string. Okay, so we see each one of our tokens being printed down here. Okay, just wanted I know this isn't 100% correct. I just wanted to show you guys that you can use int string to decode the integers back to words if you want to see what it's like. So our target is essentially going to be one time step forward of our train, of our input, right? So here, because we want to predict the next time step, our target is going to be the same thing as the train, but just moved one time step forward. And that's what we can see when we compare each of these together. So we can see that all of these have moved up by one, right? So here we have 13,142, 1995, and this is all moved up to 14,511. And we're working with sentence length time or T by B here, which is why if you transpose this, you'd be able to get something that you might be able to understand a bit more. But this is just working as intended with the T times B variant that we have. Okay. So we now get to this second definition of an RNN class. So we're forgetting about the RNN class that we did earlier on, and we're defining a new one. So I'm going to run through this with just RNN. Afterwards, we will take a look at LSTMs and show the same class just working for LSTMs and a manual LSTM that we're going to build up. Okay, so we're just going to assign the variant, which in this case is just going to be this RNN flag. So I think that's here. And the embedding layers, we're just going to load them from the glove layers that we had earlier on. So we can only use unidirectionality here because we don't have access to the whole sequence when when we're modeling, right? So when we're modeling, we want to use only the previous words we've seen to predict the next words. So we can't, by definition, we can't look into the future to look at those words. here we were allowed to do that because we were trying to classify a movie review, right? So the whole sequence is given to us already, and we can use this whole sequence to classify the review. But with a language modeling task, we don't have access to the rest of the sequence because this is what we're trying to predict. So we can only use unidirectionality here. So there's some code that you guys are going to have to fill in, and I want you guys to do that after I finish running through this. So if variant is RNN, which is what we're doing, I want you guys to initialize the RNN class. Make sure you pass in batch first is true, because we're going to obviously be using a batch first to conceptually understand things a bit easier. Then we'll have the output layer. So you need you guys to initialize this. And basically calculate the logits, and I want you to apply dropout when you calculate these logits as well. Then initialize the optimizer and the criterion. So again, this is going to be a multi-class problem because we're going to try and categorize into we want our network to predict one of the things out of the length of our vocabulary. Okay, guys, if you take 10 minutes to do this, make sure you understand the code. Obviously, feel free to ask questions. And yeah, check out groups as well. I'm sure there are people in there helping other people out, and to those who are in there, thank you very much, and hopefully you guys can have some interesting discussions around this thing. So we'll come back at 25 past.
What's a good way to describe the different views of, like, when you're in the class, you can either
Alright guys, welcome back. If you guys can answer in comments about any answers that you might have been able to come up with during that code break, that'll be really good. Okay, so we're gonna initialize our RNN class. I'm gonna do nn.rnn. And it's basically going to be the same as this LSTM class. So we have it as input embedding dim, because that comes from here, and going to change that to hidden dim, or each one of our hidden states is going to be of hidden dim, and batch first is true. Okay, and our fully connected layer. Anybody have an answer for that? Just wait a second for, to see if anybody has an answer to this fully connected layer before I type it out.
Yeah. Could you add me as a group admin in AI Core? Or just add Kelly?
Yes, nn.linear, but linear what? Well, what are the arguments we're passing in? Cool. Thank you guys. Good answers, because they're all correct. So self.fc equals nn.linear hidden dim to output dim. Okay, and what about our logits with the dropout I mentioned? Whoever answered this with the optimizers, you're correct, so I'm gonna stick that into its relevant portion. Num layer 1 is already specified by default, so if you look at the documentation, it will initialize number of layers to 1. The reason I showed it earlier on was just to let you guys and to inform you guys that you can have RNNs and LSTMs and other types of RNNs have more than one layer, and those are called stacked RNNs. We're not really going to use them here. We don't need to use them here, so it's done by default. Okay, interesting. You squeezed 0. Let's see if that makes sense based on the shapes. No, I'm not sure your code would work because you can't squeeze index 0. All hidden is going to be of batch times t times d times number of directions. So if you wanted to use this, you would need to refer to like all hidden, everything along the batch dimension, everything along the time dimension, and just the last entry in the oh sorry, and everything along the last entry in the time dimension. -1 there. So if you wanted to use all hidden, this is what you'd have to do, and this is the same as last hidden. Okay, so we're just going to use last hidden because we don't need to write out that code basically. Squeeze by passing in an argument of 0 will actually throw an error if you try to run it, because it's going to try and squeeze on a dimension which has more than one element in there. So logits, self.fc, and correctly dropout is within that applied to the last hidden state. Cool. Initialize this. Good job on the optimizer and criterion. And one thing we need to do when we're doing language modeling is detach the hidden state, because we're going to feed in this hidden state as an initialization to and I'll talk more about this talk a bit more about this in a second, but we're going to say, okay, make this prediction and then initialize this RNN cell with the previous hidden state. And we want to save this hidden state, but we don't want to backprop through it. Otherwise, because we're already going to backprop through it to the beginning. Otherwise, it will backprop through to the beginning of the data set, which is obviously 2 million long, and that's not what we want. So we're just going to detach it, and then we're going to save it. Okay, so the way we evaluate language models it is kind of difficult, because there isn't like one source of truth, and a meaning can be expressed in many completely valid ways. Obviously, human evaluation is what we would is kind of like the most reliable, but it's very expensive, and it's very slow as well, because you have to say, okay, send this to a human. Okay, does this look like a valid sentence? Yes. Okay, cool. Now we have one feedback, and obviously that's quite long. So we use this metric called perplexity, and all this says is, does our model prefer real sentences to rarely observed ones? And these rarely observed ones, typically could be ungrammatical or gibberish. And the way we do this is basically by exponentiating our entropy. And that's literally it, right? The perplexity is the exponentiated entropy. So we have our loss, which is the entropy. So we remember cross entropy. We have our loss. So all we do is we just send it to an exponentiation function and return that. Did my stream cut out? Just gonna refresh the page. Okay, cool. All right, and now we have our train loop. So I'm gonna stick the optimizer in the train loop, so we don't have that issue that we had before. Okay, so for every epoch, we're gonna obviously put our model in train mode, and we can ignore this is LSTM for now. Just focus on this prev hidden. So we're gonna create like a tensor, which is going to be in the shape of last hidden that we saw earlier on, I believe. Yeah. So what we're doing is we're initializing a tensor of zeros to this shape of last hidden. So because it's unidirectional, because we only have one layer, this is 1 times batch size times hidden dimension size, or D. Oh, there we go. Cool. Okay, so we just initialize a vector to zeros. Okay, and now we're gonna loop over our train batch, our train iterator. So for every batch in our train iterator, we're gonna zero grad the gradients. You guys will need to load in the text and targets and feed it to the model. This line will give you a bit more, when you read through this code, this will give you a bit more information about what the save hidden is doing. And when we come back, I'll talk about that a bit more. So we want to compute the loss, and we're going to reshape our outputs to eliminate batching. Again, if you guys have any questions on this, this part here, I can run through it. Let me know. And then we're going to backprop the average loss. And I want you guys to think about why we backprop the average loss. Finally, I want you guys to call the optimizer and perform gradient descent itself. Then we just compute the train loss per token and the perplexity, and that's it. You guys will also need to, we can leave this evaluation method for now, and after we do LSTMs, we can come back and I'll get you guys to fill this out. But if you guys can get this successfully training, and we'll come back in 10 minutes and talk about LSTMs after, talking through this a bit more. Alright guys, we're back. So I think we were gonna implement this train loop. Does interesting. Okay, let's see if we get the same error as well. So what did you put for text and targets?
What these are called messages. Route keys. Route keys, and these are basically. If you go back to that page, you can see I've got this thing called route selection expression, which says when the action basically specifies what route we're going to look for. Yeah, exactly.
So I'd imagine
so yeah, you can add a new
text to be batch dot
need them to be like
text dot t.
or whatever.
Obviously, if you're training on GPU, dot to device.
If you click on one of them, you can see how it's
And targets would be so it's tuple of tensors, text and target. So targets would be batch dot target dot.
see similar to
I
I
think we're going to transpose this.
which goes to
Alright. Oh, so yeah, so here we're just going to load in the batch and target, and here it will we'll have them both reshaped, and we can stick them to device.
with all the requests to the website.
Okay, so for each batch, we're going to detach the hidden state from how it was previously produced, and we need to do this, otherwise the model will backpropagate all the way back to the beginning of the dataset. So we're just going to save this prev hidden. So we pass in prev hidden to this save hidden function, and
Class members, for example. This is like
because it's going to be a torch.tensor, we're just going to detach it and return the detached version. So this is basically the same as just doing prev hidden equals prev hidden dot detach.
and then you just do you send them this message.
And for our first loop, we just have this initialized prev hidden, which is just zeros, which is what we pass into
Dispatch form, and then displays that on the model to them.
to our model.
And then this is the actual posting to that connection. Done.
Okay, I'm gonna run out the code in a second. I'm gonna see if I get the same issue that you're getting. So we run the model, and our model is going to take two inputs. Okay, so it's going to take the text and the previous hidden, and when we run the RNN, we're going to pass in the previous hidden state. So the forward method of an RNN. So up here we saw we just passed in one argument to the RNN. But the RNN also has another argument we can pass in called init hidden, I think. I'll just take the documentation for that.
That's basically that handles these things. So it's just what you optimize.
Okay, so
Yeah, it's not that, but
it's different.
I always do send back the same one just to keep it.
I wish it would just
consistent,
link me to the
so
docs.
Like teacher will send an action like dispatch form, and then a student will receive a dispatch form, even though they're not dispatching form, just to keep it in sync, so we know which lambda function is referring to, that kind of thing, right? Yeah, just convention. That's what I tend to do. So yeah, it's like, up to you however you do it. You need to put in a case for add to feed or whatever. And
Okay,
then
so
you need to somehow
our input is the initial hidden state for the first batch.
Sweet.
Okay, so we can pass in two inputs to our RNN, and that means for every batch, because we're passing in the previous hidden state, we're passing in this HT-1. Every RNN cell is going to be using this previous hidden state. If we didn't detach, we wouldn't have needed to pass this argument in, but because we have detached, this is necessary. Anyway, so we get the all hidden and last hidden, and we've already run through this section where obviously we just pass in the last hidden to the fully connected layer. Okay. So we have our model, which we're passing in through the arguments, obviously, in our train model, and what we pass to our model is, see if there's any answers for this. is our text, so text and the previous hidden. Now we reshape this to match the shapes we want our the shapes that we expect our criterion to take. So we can take a look at the cross entropy in there so you guys know what shapes we're expecting when we pass in the arguments. So the predictions versus the ground truth. If you guys managed to take a read of that, that's cool. If you didn't, I definitely recommend taking a read of that and then asking me any questions about why we do this. And then we just want to backpropagate the average loss because we can do two things with the losses. We can either sum them up because we're doing this over time, right? So we have a loss per time step. We have a loss for this word, we have a loss for this word, and we have a loss for this word. And we want to get the loss over the whole sequence. So we can do this in two ways. We can either sum all the losses or we can average all the losses. And that's all we're doing. We're averaging the losses here. And then we can call the optimizer. And this is obviously done by, sorry, not call the optimizer. We want to gradient descent. So we just do optimizer.step. And we work out the epoch loss and whatever. So then we work out the train loss per token, and we're simply doing this by doing the average loss per token because this is summed and we're just dividing it by the number of items. So this is like the mean loss. Alternatively, we could have had this loss per words and then feed it in loss by loss into the perplexity, but we just have this this one loss, average loss per token for our whole sequence. So we feed this in and this will return our perplexity metric. And perplexity is better if it's lower. So the lower the perplexity, the better. Okay, this evaluate model will work fine. Line 16, torch.nograd. Is this where you were getting the error? Somebody mentioned about an error in with an indentation. So what I'm going to do is just remove this because I think that's what's causing the error. Actually, no, I'm going to comment this out and then there shouldn't be an error. Okay, so this is the target batch size issue that we got first of all. So let's look at what targets is. So we'll just say after we've reshaped it. So we know that this batch size is wrong, but let's print it. Okay, interesting. So targets is 64, but for some reason our network is saying it's, or our train loop is saying it's 1920. So the reason why that's happening is because we've flattened everything here. So if we look at shape inputs to eliminate batching, dim. Okay, let's look at what our logits are. And if we do this, logits.view -1 output dim, so we're just printing the shape of this, and we'll print the shape of targets.reshape as well. So sheep. Interesting. Okay, so we have something which is 64 times 300 or 33,000. So this is going to be our vocab size. So the logits is going to be like essentially not a one hot vector, but our logits over the vocabulary size that we have. And we actually want this to be in 64.1. So it's the targets which are the issue here. So let's see what targets.shape is going to be b times t. So t is the sequence length, because we have a target for each individual word. Okay, I'm just going to check the solutions file to this to see if anything is different now. Oh, why am I downloading the language server? Interesting. Just open this in the notebook. Oh, the same thing here. Interesting. Okay, this will probably take me like a good couple of minutes to debug. What I'm going to do is I'm going to move on from this, talk about LSTMs, and we'll take a code break in a bit where I'll try and fix this. Okay, we're not going to have enough time to get to the sequence to sequence stuff today, but that's fine because we ran into a similar issue last time and we just managed to continue starting from sequence to sequence. So our next lecture will start with this, and we'll spend the next time we have, or the remaining time we have to talk about LSTMs. Okay, so there's an issue with RNNs called the vanishing gradient problem or the exploding gradient problem. It works either ways. So the vanishing gradient problem is that the gradient signal gets smaller and smaller through time as the backpropagation continues on. So what this means is that the longer the sequence that we have, the smaller the signal of the gradient as we go back in time. So given this RNN here, we work out a loss and we want to backprop against all the weights. But because all of these hidden states rely on hidden states which come before, it's quite easy to lose the signal because we're backpropping through so many time steps. So this is an issue with RNNs, and even like the 32 length sequence that we saw earlier on with the movie reviews, that's kind of too long for just a normal vanilla RNN to process normally. So if the gradient does become vanishingly small, we can't capture the pass correctly. And there's an example here. So a patient with a rare sarcoma of soft tissue was on the left thigh was presented to the hospital yesterday. Was presented along with the context of who we're talking about that was presented, is separated by 11 words. And for just a normal RNN, this is quite a lot. So we have LSTMs, or short for long short-term memory architectures. And these are kind of like a complicated function which helps, which mitigates the vanishing gradient problem to a certain degree. And I can understand how, like, looking at this like for the first time, you're like, what the hell is going on here, right? We have like 7 equations and we got all these things going on here. But actually, when you kind of break this down into its raw components, there is intuition behind there, and that's what I'm going to run through with you now. So the key to LSTMs is the cell state, which is this C, which is running through this entire top branch of the RNN cell. So the RNN cell here is an or RNN stands for recurrent neural network, and the cells that we use can be of like a vanilla RNN cell, which was what we just saw earlier, an LSTM cell, a GRU cell, or any other kind of recurrent cell. So the difference between this and what we saw in the RNN was that the RNN just had a hidden state, right? HT. We also have a cell state, CT. And you can think of cell state as like the internal hidden state, so it's only relevant to the LSTM network, whereas HT is the external hidden state, which we kind of expose to the outside world. So any predictions that we do will be based on HT, and the CT is just carrying on processing through, is only used for internal computations within the LSTM cell. So the LSTM also has the ability to add or remove information from the cell state, and gates are a way to let this information through. So what a gate is it's a sigmoid neural network and a pointwise multiplication operation. And there are 3 of these gates. So I'm going to talk about something called the forget gate, and we're also going to look at the input, candidate, and output gate as well. So let's talk about how to read this, and the kind of intuition between what it does, which is spoken more about in this diagram. And actually, I'll just read it through the diagram. Okay, so the forget gate. So what we have as input to one RNN cell or one LSTM cell is the previous cell state, the previous hidden state, and the input. So the input is concatenated together with the previous hidden state, same way that it was done in the RNN, and this is all fed to something which is called the forget gate. And the forget gate decides what information we're going to throw away. So it does this by outputting a value between 0 and 1. If it's 0, we forget that information because there's an element-wise multiplication going on. If it's 1, it means we keep that, we're more likely to keep the information. So the element-wise multiplication, which you see here, okay, so there's an element-wise multiplication at this point up here. So remember, we want to keep track of what CT is doing and what HT is doing, because these are going to be the outputs of our LSTM cell. So we feed our input, so this concatenation of the previous hidden state and our input into the forget gate, which is a linear layer, right? Followed by a sigmoid nonlinearity. And remember, what sigmoid does is it squashes values between 0 and 1. So values which are close to 0, when from the resulting of this this equation, which you can see here, if these values are going to be close to 0, then those relevant values are going to essentially kill that value in the cell state. If it's close to 1, it means we're going to retain that information that we keep. We then have, looking at the next thing, an input and a candidate gate. So the input gate decides what new information we're going to store in the cell states. So this again is a sigmoid multiplied by some neural network over the input, which is XT and HT, and some bias. So note kind of like the relation of the maths here versus what I've written here. Okay, so this is the pure maths, and what this says, the pure maths says that we're learning 2 different weight matrices, one for the input based on the forget gate, and one for the hidden state for the forget gate. Right, so that's this F is forget, and I is input, and H is hidden. So we have plus some bias relevant for the forget gate. And this is translated over into something which we can work with a bit more easily. So we have a linear layer, which is, you know, a weights matrix multiplied by the concatenation of our hidden state and our input state. So this is the trick that I described at the very, very beginning of this notebook with the RNN. This sigma is a sigmoid, and the shape of this weights matrix, so our linear layer can be decomposed into a dot product of a weights matrix and the input plus some bias, and the shape of this weights matrix is going to be the hidden dimensionality plus the embedding size of our input, and it's going to change that all to the hidden dimensionality, right? So this is essentially saying that we have a hidden state and the input which comes in. So the size of this, what's fed into this non-linearity is going to be hidden size dim plus input dim, and we're going to output something which is hidden dim. Okay, so let's look at this. Let's look at this a bit more visually. So our input gate is going to be very similar to our forget gate, but this decides what information we want to retain, or what information we're going to store. And then we also have something called a candidate gate. Now the candidate gate, instead of being a sigmoid, it's going to be a tanh activation function, which squashes values between -1 and 1. And we're going to use this to create like this intermediate representation by multiplying the input gates, the values of the input and the values of the candidate together by an element-wise multiplication, which is done here. So okay, this is probably the better one to look at. So this intermediate cell state, which is represented by C dash, so we take in CT minus 1 and we work out some kind of intermediate cell state. So we're here now, so that's going along to this addition operation, and we're adding in the element-wise multiplication of the input gate and the candidate gate. And sorry, this should be in blue, not green. So this is the candidate gate. So as I mentioned, we're going to decide what information we're going to store, and it consists of 3 gates: the input gate, the candidate gate, 3 parts, sorry, and a cell state update. The input gate decides what values need to be updated by using a sigmoid neural network, which is what we just saw earlier on, the same with the forget network. And the candidate gate decides how these values are going to get updated, and it does this using a tanh nonlinearity. So the new cell state is just the aggregation of what we've forgotten and the new information that we need to memorize. And finally, we're going to go to the output gate. Now note that the output gate is mainly focused on outputting the internal hidden state, the external hidden state. So this is done by again a sigmoid nonlinearity, and then done by a element-wise multiplication between the cell state passed through a tanh function. Okay, so this tanh is going to squeeze values from the cell state in between -1 and 1, and then we're going to have an element-wise multiplication between values which range from -1 and 1 and values which range from 0 to 1. So the new hidden cell state is essentially a filtered version of the new hidden state, HT, is essentially a filtered version of the cell state. The cell state forces its values between -1 and 1 by a tanh, and this value, this tanh value, is element-wise multiplied by the output of the output gate, which is a sigmoid neural network. So here we see a sigmoid neural network, and here we just see the operation that we apply to the cell state that we have to get our new output gate. So this helps the vanishing gradient problem, because when our RNN computes the new hidden state from scratch based on the previous state and the input, the LSTM computes the new hidden state by choosing what information to add to the current representation. And this allows basically we can say some information is irrelevant and some information is relevant, so our gradient signal is going to be able to reflect that. And they're going to be trained by the teacher forcing methodology I described earlier on. And what I'm going to get you guys to do is actually code this LSTM up from scratch. Okay, so we're going to have a manual implementation of an LSTM, and that's this code cell here. I'm not going to run through this code. I want you guys to try and understand what's going on. And I'm going to give you guys until, because it's a bit more complicated, I'm going to give you guys until 25 past to actually code this up. So you can look at how I've done the forget gate, and similarly you guys will need to do the input, candidate, and output gate. And again, look through the code to see how we're actually running it. The double pound sign means that this is where you'll need to fit in code. Let's see any questions. Yeah, again, feel free to visit groups. Feel free to ask questions on here, and I'll be able to get you an answer.
chat. I think, yeah. You
Okay,
just call
welcome back, guys. Been googling around for this this issue. Well, I tried to fix it first of all. Wasn't able to fix it in time. Did a quick Google at the end. Seems like the code is right. So after this session is over, I'm gonna take another look, and I'll send a message across all of our channels and update the notebook. So I basically trained this code that we see the results
The
for
lambda function which I made yesterday.
down here.
Change that to putting in
On GPU, so I have like the original code I used to train it, and in there I can see like we're calling logits.view and target.reshape in the same way. So gonna take another look at that, because obviously this this should work as basically intended, right? But yeah, I'll take another look at that and I'll get back to you guys on that. Yeah, I've been experiencing this slow Jupyter as well, so I just refresh. I think that will fix it, clear the kernel. It's quite a lot of data we just downloaded and are storing in memory, so that's another reason that we could have this issue. Okay, guys, let's get started on this manual LSTM. Have you guys got any solutions for the input gate, candidate gate, and output gate? So we remember that the input gate is quite similar to the forget gate. And if we look at the parameters that we're passing in, just input size and hidden size. So we're going to have a sequential of sigmoid of nn.linear, hidden size plus input size. This goes to hidden size. And a activation, which is sigmoid. Ah, cool. Whoever sent this, you're a legend. Let's see if this works. Definitely need to get a code view in here. Forget gate, input gate, sigmoid, candidate gate. Output gate, cool. So this looks correct to me. Tan H, nice. Congrats. And linear layers, sigmoid for the output gate, which is here. Awesome, yeah, nice. Congratulations. Well done, I should say, rather. Okay, so we take in our input and the previous hidden state, and at the initial time step, so when t equals 0, we're gonna say that the initial hidden state is going to be 0 and the initial cell state is going to be a vector of zeros. So our LSTM actually returns two things. It's going to return all the hidden states, HT, which is the last hidden state, and CT, which is the last cell state. Which is why we have this HT and CT up here. Okay, so XT is the teeth sequence element along our sequence dimension. So this will be the first word, the second word, the third word, or something. That's what this is referring to. And we now want to concat that with hx, so this will form our input. So this is what this concatenation operation is going to do, and we're going to use this concatenation as the input to all the gates. Guys, feel free to post the code that you've put here, and I'll see if it's correct or not, and I can give you feedback. So we gotta concatenate the two together. So we have xt and we have ht. Okay, so we do torch dot. See if anyone's put that code in. Nope. I'm gonna give you a little upvote though. Torch dot cat, and we pass in, can't remember the syntax, I think passing it in a tuple, and that's ht and ct, ht and xt rather, along the last dimension. Then we feed it through to this concat hx through the forget gate. Feed it through. Then we want to work out c prime t, which is our intermediate representation. So c prime t equals the previous cell state minus element wise multiplied with ft, which we've just calculated. So we have ct and this is the element wise multiplication ft. I think that's right. Just double check to make sure we don't use pref hidden. Yeah, ct element wise multiplied with ft. Candidate t. So we see the input gate. Just feed that in with the concats. And the candidate gate is going to be this blue thing here. So we have a tan h nonlinearity, so we're just going to call our candidate gate. So self dot candidate gate of the concats. We then have our new cell state, which is going to be the update, which I'll put here. So update, so that's going to be ct equals c prime t plus the element wise multiplication of it and candidate t. So c prime t plus it times can t, and finally the output gate and the hidden gate, the hidden state rather. So the output gate is self dot output gate of concat hx, and the hidden gate is going to be the output gate element wise multiplied with tan h cell state. So ot times nn dot, or how to do this, f or nn. Okay, torch dot tan h of the cell state, which is ct. Then we're going to return the I'm going to say this hidden states list, which is initially going to be some zeros. We're going to populate this hidden state. So what we're doing is we're looping over every t in our sequence that we're feeding in. So this LSTM is going to receive x as b times t, yeah, and we're looping over each one of these, each one of the times dimensions. So for every word in our sequence, we're calculating an intermediate representation, so xt or ft, ct, whatever, right? After we exit out this for loop, we have all of our hidden states, and at every for loop we're saying, okay, this is what our hidden state tensor is going to be. So for the teeth dimension, update it with the value of ht, which we just calculated, and then we return this along with the last hidden state and the last cell state. So that's for the last word in the sequence. We're returning this cell state and this hidden state. Okay, and then we can create our manual LSTM and our LSTM in the same way that we did previously. Here we're just passing in the where's that issue coming from? Variant manual LSTM, name hidden is not defined. Okay, so this should be hidden size, sorry. Okay, so now let's walk through the LSTM part of this RNN style that we described, RNN class that we defined earlier on. Okay, so a normal LSTM is basically initialized the same way as the RNN. There are a couple of extra arguments that we can pass in, and again, I'll definitely refer you to the docs to take a look at that. And the manual LSTM is the LSTM that we have just coded up right now. Also, great job if you managed to follow that, guys. Like, I remember when I first saw the LSTM and saw its equations, like the kind of what operators it does to work as a function. I was just like, what does this even mean? How am I meant to interpret that? But you guys have literally gone from not knowing what an LSTM is to implementing one in Scratch. And honestly, I can say that's a skill that very, very few people have. So big kudos to you guys if you're managing to follow that. So if the variant flag that we pass in is manual LSTM, we're going to initialize our manual LSTM with embedding dim and hidden dim as the arguments. We don't need to pass in the batch first true because we just coded this manual LSTM and we're just assuming that the inputs that we pass in are going to be in batch first order. And actually the rest of how we use the LSTM is quite similar. So this is the only part where you have to pay attention to. So we're assigning these variables to self.rnn, or these objects to self.rnn. And remember what I said, then LSTM returns, it has all the hidden states as the first argument, and as the first thing it returns. And the second thing it returns is a tuple. And this tuple has hidden state and self state within it. Okay, so this is okay, for a LSTM, last hidden is a tuple of HT and CT. And the shape of HT equals the shape of CT, which equals, this shape here, num layers times B times T. I think it's correct. Might be D though. Yeah, it's D, not T, sorry. So this should be D. So just to make that a bit clearer, the hidden state is of size num layers times num directions, where layers and directions is just one in this case, times batch times D, and D is the hidden size of of our network, and that has the same shape as the self state. Oh, it's just called manual LSTM because we implemented that from scratch. So this is like our manual implementation of an LSTM. The actual PyTorch LSTM, even though it performs the same mathematical operations, the code is a lot more optimized. So I think in these screenshots that I'm seeing, we can kind of see that. So I'll walk us through that now. So unfortunately, I don't think we're going to be able to train this because of that issue I mentioned in the train loop. I am going to take a look at that once we're done here, and we can try and sort that out. Drop out argument input must be tensor not tuple. Here we pass in the optimizer as a function, but I don't think that's where the must be tensor not tuple. Oh, okay. So here we want to work out the so if our self.variant equals LSTM, or if self.variant equals manual LSTM, our last hidden is going to be the cell state. Okay, so this returns a tuple, as I said, and we the hidden state, sorry, and we only want the hidden state to be the last hidden, so we just extract that out from our last hidden. Sorry, and this is Python, so okay, and then So it's the exact one. Not 100% sure what you mean by this. Might be referring to something I said earlier, but if you could just clarify that, then that would be quite nice. And this last hidden should be this now, so just redefine this train loop. Cool. Okay, so we have this same error that we're seeing before, which I said I'll get back to you guys regarding that. And we should see that same error for the LSTM, which we do. But under the assumption that we've got these errors working, if we were to train them, I had to train these on GPU because they take too long to train on CPU. We can look at how they fare up against each other. So remember what I said, that the lower perplexity, the better. So we're saying here that this is the vanilla RNN. And sorry, I couldn't make this prettier. They have to be screenshotted from terminal. So we start with like a incredibly high perplexity, but as we progress down through the epochs, we see that our perplexity gets lower and lower. So this means that our model is able to produce a lot more sensible outputs. Our manual LSTM starts at a similar level, starts slightly higher at 612, and we can see that it drops considerably lower than the end of it though, okay? So we see that, this is 270 for a normal RNN, and this is 201 for an LSTM, and it doesn't look like it has any indication of stopping there either. It looks like if we continue training, then this will still drop. So we'll take a look at the normal implementation for the LSTM, which is where we just pass in this variant and we initialize it as self.rnn equals self.lstm. And we can see that our perplexities are actually quite similar, right? We start at 600 and something and we drop down to about 200. So here we have 201 and here we can have 199, but that can just be explained by, just the initialization of the network and the fact that we're only training for 5 epochs. So this is really cool, guys, because we've just built our own LSTM, which performs as well as the LSTM from PyTorch. The downside from our LSTM is we can see the execution time per epoch, and that's 56 seconds approximately. We see that this is almost cut by a third for the actual LSTM. It's kind of similar to the RNN time, so they've actually managed to optimize the LSTM to be just very, very slightly slower than an RNN, which I think is an absolutely crazy feat, considering how much more complicated the LSTM is than the RNN. One more thing I want to talk about before I call it a day is GRUs. Let's check for any comments. Yeah, so the two LSTMs give us the same results because that's what they are, right? They're LSTMs, so we should expect similar results from the same function that we're calling, right? If we trained our network on a linear layer from PyTorch and a linear layer that we wrote up ourselves, we'd expect the results that we get to be comparable. So a GRU, or a gated recurrent unit, combines the forget gates and input gates into one single update gate, which is Z. So this is Z here. So we only have two gates really, a reset gate and an update gate. So this Z and this R for reset. And it also merges the cell state and the hidden state and makes another small couple of changes, and the result is simpler than or slightly simpler than the LSTM model. So guys, if you've I'm not going to show you how to code this up or implement it from PyTorch, but the actual way that you would use this is nn.gru. So instead of nn.rnn or nn.lstm, we can use this nn.gru. Again, it takes in the same arguments as LSTM, and then we'll just say like self.rnn equals nn.gru or self.gru equals nn.gru, whatever you want to call that variable, that's fine. But I'm not going to show you how to code this up from scratch. And actually, I think it's an interesting challenge that if you can, now that you know how to code the LSTM up from scratch and how the maths that we've seen from the original LSTM equations, so not the ones I have on the pictures, the ones that are in text here, how they translate to something that we can actually use in code. And then we coded that up. So as a challenge to yourself, you guys can do this with a GRU. So here are the equations for that. You can go around, you can search on Google as well if you want. If you do it and you want me to take a look, then yeah, feel free to send it over. You guys are part of the AI course, so you know how easily contactable we all are, but that'll be really cool. So next lesson, I'm going to call it here because we've been at this for almost 4 hours now. For the 10 guys who are stuck through, thank you very much for sticking through.
Respect.
Yeah, respect. And we'll look at sequence to sequence from the start of next lecture. Cool, guys. I'll be on the chat for a couple more minutes, just answering any questions that you got. So feel free to throw them my way. All right, bye, guys.